you mentioned that our universe is a very weird place. So returning to that, and at long last, now the basics of string theory. And I'm going to leave M theory and 0/2+ dimensional branes aside for now, unless you think it's important to introduce, though. But for the time being, just one, what is a string? And then how basically are they to be reconciled with the already extremely 14 decimal point successful standard particle model? Or to put it in other words, what's the relationship between strings and point particles?
Well, so one of the interesting things about string theory is that it can be described from many different equivalent viewpoints. There are many different ways of arriving at string theory. It's kind of like all roads lead to Rome. People have tried to construct theories which general, and there are many different descriptions of it. But the first one involves strings. And it's an odd thing that we still call, that it is still called, especially in the general public and general discussion, that this big theory is still called string theory. Working theoretical physicists like myself don't use the word in quite the same way that it's used in the press, because the part that is directly related to strings is only a small piece of this big mathematical structure of the space of possible quantum field theories and general relativity and black holes and all these different ideas, which are not separate ideas, but are tied together in many different beautiful ways, often involving profound mathematics. And so string theory is just a little corner, but somehow that corner has the whole enterprise of the majority of what theoretical physicists and mathematical physicists have been doing for the last 40 years has been lumped together under the heading string theory. Okay, but it did start as the idea that if you replace, in quantum field theory, which is the theory that's been tested to 14 decimal places, the basic object is a quantum particle which moves around and interacts, and they scatter electrons and protons, they make up atoms and everything. So that these particles, actually, if you had a very, very powerful microscope, you could see that they aren't actually point-like objects, but they're little loops of string. And loops of string, and this weirdly solves the infinity problem. This makes quantum, this just replacing, well, in a very specific way, there are very prescribed rules about how you do it, but replacing the notion of a particle with a string leads you to a theory without the infinity problem that Pauli had. So that's what a string is. Now, a string can do different things, right? If you have a little string, So particles don't have much structure. They might have a spin that could point up or down, or a charge, but they don't have a lot of structure. But strings can do all kinds of things. They can, vibrate in a figure 8, or they can do this, or they can do that. And if you look at it from far away and unable to resolve that fine structure, what has been amazingly shown is that the strings can, to the observer who can't see the fine detail, the string can masquerade as any one of the particles in nature: the electron, the quark, the neutrino, the photon, even the graviton. So that's a really very striking mathematical fact that the string, the costume closet of the string contains costumes which look like everything that we've actually seen. Now, this doesn't mean that the world is made of strings. It just means that it's a logical possibility.
And I think you mentioned that when we were talking about point particles, they don't resolve into anything. They just look like points, but they have some other qualities like mass and charge and spin. And I'm wondering how the mass and the energy, for instance, of a string's vibrational pattern are connected, so that we end up, if it vibrates in some certain way, we have a particle with a mass. If that question makes enough sense.
No, totally. Yeah, I wanted to use another analogy. It's like, a guitar string, right? You pluck the E, the top string, the E, and it makes a certain note, and then you put your finger on the fret and pluck it. It makes another note. So one string, guitar string, vibrates, interacts with the air, sends out sound waves. One string is capable of sounding different, can make many different sounds. In fact, if it were a really good string, it could make infinitely many sounds, because there are infinitely many, a perfect string. There are infinitely many harmonics. It could make infinitely many different sounds, higher and higher harmonics. Similarly, a fundamental string in string theory, depending on how it's vibrating, interacts differently with light, and it will look different. So that is how a string can look like different particles. Now, you just asked me, how do we relate these things? Well, there's a formula. It's a complicated formula. It's a very, when you teach a course in string theory, they have to have had quantum field theory and relativity beforehand, and then it's a couple of weeks before you could write down that formula. But there is definitely a formula which tells you exactly what the string does.
Okay. And there are two deeper questions here that I have. So I can understand how, so bosons are the sorts of particles that carry what we think of as forces. So photons are the bosons for the electromagnetic force. And I can understand, given the picture you've just described, how a vibrating string will manifest as a photon. But something that I don't understand is, if in the standard model, the Higgs boson is what gives particles their mass, how a string independently of the Higgs boson, so a string that will become an electron, can have a mass independent of the string that represents the Higgs boson? or and again, maybe this question might be confused because I haven't read anything about this question. It's just something that occurred to me as I was reading and thinking. But maybe you can elaborate or tell me that I'm just mixed up somewhere.
Well, I don't think the answer to this question is very different in quantum field theory than it is in string theory. In other words, there's a limit of string theory. There's some limit in which you just look at, you sort of think about the theory on longer distance scales where you can't see the strings, and then it reduces to quantum field theory and what we know and love. And if you wanted to explain how the Higgs bosons give particles a mass, it wouldn't buy you anything in string theory. So string theory can have Higgs bosons, and the Higgs bosons can give masses, but those are all, the basic reality in string theory would be the strings, and other things are approximate, right? So, and they're only in some approximation scheme do they make sense. And so, if you were trying to answer this question, the answer wouldn't really be different. It wouldn't use string theory. It would just use the usual ideas from particle physics. You would reduce the string theory system of equations to the particle theory ones, and then you would just sew in the particle theory explanation.
Okay, and then my last mass-related question is the mass of the particle that is a string is determined by the vibration of the string. Does it just make no sense to ask what the mass is of a non-vibrating string?
No, that question makes sense. But it would depend. I mean, I'm taking a little bit of liberty here in translating your questions into a more precise mathematical one. But I think that you could say that the massless particles in nature, like the photon, the graviton, they're examples. They can be thought of as examples of strings that aren't vibrating in their kind of lowest energy state.